Hello, today we're going to talk about the derivative tests, both the first and second derivative tests. Let's look at the first derivative test. Let C be a critical number of a function f that is continuous on an open interval I containing C. If f is differentiable on the interval, except possibly at C, so this could be a point of discontinuity, then the function value at C can be classified as follows. If f prime, the first derivative, changes from negative to positive at C, then f has a relative minimum at C, f of C. It's a point that is the minimum. If f prime of x changes from positive to negative at C, then f has a relative maximum at the point C, f of C. If f prime of x is positive on both sides of C or negative on both sides of C, so does not change sign, then f of C is neither a relative minimum nor a relative maximum. Now, to really understand these, let's take a look at a couple of graphs. Looking at the first one, if f prime changes from negative to positive at C, so this is the sign of the derivative, here's our critical number C, then we have a relative minimum. Why is that? If the sign of the derivative is negative, we know the graph is decreasing. If the sign of the derivative is positive, we know the graph is increasing. And in drawing these arrows, it's fairly easy to see that this must in fact be a minimum, so a minimum makes sense in this case. Looking at the second one, if f prime changes from positive, so it's increasing, to a negative, decreasing, now we can see that we do indeed have a maximum at C, f of C. I encourage you to draw these arrows so that you can see the sign change and what it represents in terms of increasing and decreasing functions. Here, if it's the same sign on both sides, there's no minimum. It just keeps going up. Perhaps it levels off. Perhaps it levels off while going down. But there's no obvious rise or valley in our sign change, or lack of sign change, excuse me. The second derivative test also tells us some good information. So let's let f be a function such that f prime of C equals 0. So we're looking at a critical number. The first derivative is equal to 0. The second derivative exists on an open interval containing C. Now, if the second derivative is positive, then f has a relative minimum at the point C, f of C. If the second derivative is negative, then f has a relative maximum at C, f of C. If the second derivative is also 0, then the test fails. We need to use a different test or figure out a different way to determine the value. Why is this? If the second derivative is greater than 0, we know the second derivative being positive leads to a graph that is concave up. A graph that is concave up will look somewhat similar to this, and you can see it does indeed have a minimum when it's concave up. Similarly, if the second derivative is negative, our graph is concave down. Concave down will look somewhat similar to this, and we have a maximum. So the derivative tests actually make sense with what is going on. Let's look at a couple of examples. Example 1, we're going to look at a polynomial. Find all relative extrema of f of x equals x to the third minus 9x squared plus 5. We're going to use the derivative tests as needed. Because this is a polynomial, I'm probably going to use the second derivative test because polynomials are easy to find derivatives of. So the first derivative, 3x squared minus 18x, and the second derivative is 6x minus 18. The first derivative is equal to 0 when 0 is equal to 3x squared minus 18x, and see here I've factored out the 3x, and what remains is x minus 6. In factored form, we can use the zero factor property to find that x equals 0 makes the expression 0, and x equals 6 makes the expression 0, therefore making this a true equation. Now I'm going to use the second derivative. I'm going to put 0, my first critical number, into the second derivative. When I substitute 0 for my x in the second derivative, I'll end up with negative 18. The 18 doesn't matter. The negative is what we need. Negative second derivative tells me it's concave down. If it's concave down, I'm going to have a maximum. So I know I have a relative maximum when x is 0. To find the 5, substitute back into the original function your y values on minimums, maximums, points of inflection. intercepts, your y values are always going to come from the original function. The derivatives just tell us where to look or where to find the x values that are relevant. Our second critical number is x equals 6. If I put 6 in for x in my second derivative, 36 minus 18 gives me a positive 18. The 18, once again, does not matter. What we care about is that it is positive. This leads us to concave up, second derivative positive, which will give us a relative minimum when x is 6. And if I substitute 6, once again, back into the original function, I find that my y value is negative 103. For polynomials, the second derivative test is much easier to use than doing test points and finding increasing and decreasing using the first derivative test. Here's another polynomial. Find all relative extrema of f of x equal x to the fourth minus 8x cubed plus 4. We're going to use the derivative test as needed. Once again, find the derivatives. The first derivative is 4x cubed minus 24x squared. The second derivative, 12x squared minus 48x. When I set the first derivative equal to 0, I factor out my 4x squared. And I once again end up with x equals 0 and x equals 6 as my critical numbers. When I find in my second derivative that substituting 0 gives me 0, this is not positive, this is not negative, there's no concavity to describe, therefore the second derivative test leaves me no information, even on something as straightforward as a polynomial. If it gives me no information on the first one, I'm just going to ignore the second critical number of 6 and use the first derivative test. Here we go. We know that 0 and 6 are our critical numbers. So I put 0 and 6 in proper order on a number line. I choose test points anywhere in these intervals. So I need a number that is to the left of 0. I use negative 1. I need a number between 0 and 6. 0 is the easiest number to use, so 1 is the next easiest. And then I need a number that is greater than 6 to use as a test point. What this is saying is that although I'm going to use 1, any number between 0 and 6 could be used and it'll end up with the same sign in my derivative. So let's check our test points. This is the first derivative test, so I evaluate in the first derivative. I put negative 1 in my derivative, which is on the previous page, 4x cubed minus 24x squared. And when I evaluate, I'll have a negative 4, and I'll have a negative 24, and whatever that number is, negative 28. All that we care about is that it is negative. Negative in the first interval. I put in a test point of 1. A test point of 1, excuse me, let me put in my negative sign there. A test point of 1 gives me a 4 minus 24. The fact that it's negative 20 does not matter. The fact that it's negative tells me I'm decreasing in both the first interval and our middle interval. Put in a test point of 10. When I put in 10, kind of an excessive test point here, for my x values, I'll end up with 4,000 minus 2,400. The number doesn't matter. The fact that it's positive indicates I am increasing in that interval. I have a relative minimum here, where the sign of the derivative changes from negative to positive. An x value of 6, I substitute into the original function to find a y value of negative 428. There's no relative maximum, and the critical number of x equals 0 is just a flat point. It's just a horizontal tangent line, even though the graph continues to go down. I hope this helped with your derivative tests. Check back for more videos.